appreciate about this meeting and this effort is the array of technologies that you get to see during these presentations. And so I was thrilled with the last presentation to follow that and learn something about genetic modification. I'm going to go to the other end of the technical scale and talk about just the basic concept of heating up a mass by friction. You all know that this happens. If you want to warm your hands in the winter, you just rub them together fast and you can feel the heat being generated. That's what we're going to do to fecal waste. So to do this, we're going to take a viscous material. The simulant we're going to end up using is going to be potato mix, but we've also done this with baboon feces, and I'll show you some of that data in a little bit. And we're going to apply shear stress to it, and then measure the temperature output that we get. The technology is actually well used for other applications. For example, in polymer injection molding, they'll take grains of polymer, pass it through an extruder, generate sufficient heat to melt the plastic and inject it into molds for bottles and toys and things like that. This is some data. Some of it's from the literature, some of it is for different types of materials that we've tested in our lab. There was also some data that was generated here with human stool. And basically what we were interested in looking at was something that would match this black inverted triangles. And what we've been using most for our viscosity tests has been potatoes. And just boil them up and we run them through our reactor. Rather than just building a reactor and seeing what happens, we usually don't do that for reactor design anymore. We can do a pretty accurate design by computational fluid dynamics to begin with. So that's what we did the first couple of months of this project. We took our idea and used it on a program called Console. So what we have here is basically a rotating cone inside a fixed shell. And then there's a spacing between those two, and we pass the mass between in that spacing between the cone and the shell, and that generates sufficient heating. We can get to temperatures approaching 200 degrees C that we've measured in this system. We also have the additional advantage when it comes to killing microorganisms of shear stress itself, and there's also a large pressure decrease when the material vents back to atmosphere after it's passed through the device. So we went through a series of CFD designs and we tested this. I'll show you just a couple of these, except for the color. The pictures aren't that exciting. We took an angular design primarily so that we could adjust spacing by rotating the core and the shell, adjusting them relative to each other, rather than having to build several different shells or cores and then changing parts repeatedly. We can just move a lever and we can adjust the spacing for a design variable. This one shows a prediction up to about 200 C, which was pretty close to what we got. Then we tested all kinds of things. I'm just going to zip through these. Tested the spacing. Spacing turns out to be critical. Viscosity is critical. We tested the length of the core, and how much energy you put in is a function of the contact area. So if there's more contact area, there tends to be more heat that we can apply. And we looked a little bit at angle. So we tested the variables before we went to the shop and actually built something. And this is what we built. It's got a lot of extra bells and whistles on it as a research piece of equipment, but all the action is in this central little section, and I don't know if you can see the arrow of it. Central little section right here that's about the size of my fist. And we can feed mass at constant pressure over here. This is just the feed housing. Pass it through the motor, controls the RPM. We can also measure the torque on it. And then the outlet is over on this side somewhere. We can take samples from that in this case. We've done some calculations that core reactor, that size, about this size, is sufficient to treat the solid waste of about 1,000 people a day. So we don't have much scale up to do if we're talking about small scale application. Again, this angle was just to facilitate data collection at different spacings between the shell and the core. And the gap in the shell was set up so that we could basically do that adjustment by rotating, sliding a shaft handle up and down. There's the reactor part, zoomed in a little bit. And here's some of the data that we get. The bottom line for this is normally we start off at room temperature. So it takes us about 4 minutes roughly to get up to the temperatures we need. Our goal was to get above 120 degrees C all the time. We can overshoot that, which gives us some operating flexibility. And in fact, once we get up to a sufficiently high temperature and then actually start the mass flow, we control that based on the mass flow rate based on the outlet temperature. So we're ensured that we're leaving at a condition that can guarantee that we're sterilizing the material that's passing through the reactor. The spacing needs to be fairly tight. We're doing most of our experiments at a little less than 1 millimeter for 5,000 centipoids. So we don't want water mixed in with our solid material here. We've got that with lower viscosity would present a limitation for us. A way around that is to recycle the solids. So we're doing some experiments now so that the solid that's coming out is now going into an insulated chamber where the water can flash off and leave, and then we've got a drier solid left, and then we could potentially recycle that back to the inlet, and based on maintaining a value of torque in the motor, adjust the ratio of recycle to new feed. So, key things, these should all be obvious based on what you already know about viscosity and temperature. Temperature rises, the RPM increases. It increases up to some steady state value as the hold-up time increases. Once we get everything hot, then we can maintain a temperature. We haven't looked at preheating it at all. So I guess it's possible to light a little fire under this thing before you get started, and we wouldn't have any startup time to speak of at all. Temperature increases as the gap space decreases. It says 200, but I personally have only seen 196 C on the outlet. So but the graduate students hang out in the lab more than I do. So to test this concept, we were particularly interested in looking at parasites, and Oklahoma State University also happens to be the home of the National Center for Veterinary Parasitology. So they have access to some nasty things that we can test in a controlled environment where we can test them. So we packed up our equipment and moved over to the College of Veterinary Medicine and set up to do experiments there. And we have tried this with Trichuria, and this is from a population of baboons that are infected with this parasite worm, and they're actually in El Reno, Oklahoma, for medical research done at the University of Oklahoma, and Oklahoma State vets manage the population. So we went down, got a sample of this material, and took an initial count of how many eggs were in the feces, and then passed it through the reactor and determined the destruction rate. We passed it through as is, and based on the conditions that we tested in the lab with potatoes. One of the first things we noticed was that baboons and their habits of grooming themselves and each other, these samples have a lot of hair. It's mostly hair with a little bit of other stuff thrown in. And so we could even hear when we're passing this through the system that the motor would slow down a little bit. You could hear it working a little bit harder there. And since we weren't working at such a high RPM, then our speed dropped down a little bit. So this RPM was based on power input. I don't think those RPM numbers are actually correct. The spacing is right. But you can see the temperatures that we were observed were quite low compared to what we were seeing before. And the highest we got in this, we only had so many baboons willing to donate material for this experiment, so we don't have a large number of experiments, larger than this to show you. But we got up to about 86 C, so by temperature alone, we'd think that shouldn't be sufficient. But when we took samples out and then refloated, recounted the eggs that were left, we were able to determine greater than 90% destruction of parasite eggs, even in that case. And the primary mechanism here should be the shear stress that basically ripping them apart as they're going through this system. And there's a couple of pictures of some of them after they've come out. Normally, if you've done any of these float tests from a sample, you get a fairly clean water with some eggs floating in the top. But as you can see on this left-hand sample, there's a lot of extra debris in here from these float tests. Here is a complete egg. And then we also ended up seeing some bubbles and other things in the water because this reactor will end up making the mass fairly frothy as well. So we took what we knew and we set up a different design. We wanted to make something really simple, and so we just went to the local hardware store and we bought a power drill, and we set up a one-dimensional system. So this is straight. There's still the 0.7 millimeter spacing. This drill, a DeWalt drill, can get up to about 1200 RPM, so a little bit less. But we've actually tested this as well, and we can get to, on this one, since the RPM is a little lower, on the order of about 140 C in this case. And this just has a simple plunger, feed some in, push it through. And so if you were to run the solid waste of an it still takes about 4 minutes to get up to the steady state condition, even in this case. We're not doing any preheating here. But we'd have to run it for about 10 minutes a day to handle about a population of about 10 people, the solid waste from about 10 people. So we know shear stress and temperature can be generated in this system. We think it's effective. The RPM and spacings are the keys. So we have problems with bottle caps or cloth or things like that throwing into the waste. That's going to have to be screened out. But we think we can handle viscosity issues by operating with recycle and or with the addition of paper or grass or sawdust or some other material like that. We think that this technology could be combined with other applications so that we could be in line for, let's say, equipment that's pulling mass out of a pit, for example, and sanitize it for safe transportation and subsequent handling. We're not reducing the BOD in this, so there's still some energy content in the material. If it looks like it, that's a potential application that we could integrate with. So we're interested in taking the ideas, working with other people, and seeing if we can link this technology with others. For the small scale case, we can operate it with just a car battery and a single solar panel. Since it's only going to be operating for about 10 minutes a day, we don't need to generate a lot of power to do this, but we need enough power over a short period of time to get sufficient torque to put energy in to the system. Frankly, the little drill motor couldn't stand much more than about 10 minutes of operation before it'd have to cool off. If you try to keep that thing going, it probably would burn out completely in 20 or 30 minutes. So that's where we are. We're continuing to do some experiments, and I think we're making some progress. So thank you.